In this section of notes, we're going to start looking at groups of data with two variables. So the majority of the course so far, we've only been looking at one variable. And then with two variables, we did talk about this just a little bit back in chapter 1, where we have one variable being the response variable and one variable being the explanatory variable. And we talked about looking at those root words. So the explanatory variable is your x value, it is your independent variable, it is your input, it's part of your domain. Those are how you've heard that before in other courses. And then your response variable is your y, it's your dependent variable, it's your output. So when you look at two variables, you want to know which one is more likely to impact or explain the other, and that will help make the decision. Sometimes it will be hard to tell which is which. Sometimes you will be able to figure out which is which. Now, our goal here sometimes is to try to say that one variable causes another, but that's not always possible. So we'll talk about the difference between correlation and causation. One of the first things we'll do when we look at data in two variables is that we'll make a scatter plot. One thing to remember is that scatter plots are only for quantitative variables, so not categorical variables. And one thing you also want to make sure of is that your explanatory variable is always on your x-axis. You want to make sure you have a title, that your labels and your axes are clearly labeled with a correct scale, and then you want to have each individual point plotted as a ordered pair in your scatter plot. Now here's what's new. You'll remember from chapter 1, you were asked to describe a distribution, and you had to write 4 sentences about the shape, center, variability, and outliers. Now you're going to be asked to describe scatter plots, and you also have to hit 4 pieces of information. So you want to look at the overall pattern first, and you want to look for any potential outliers. So when you describe a scatter plot, you want to give the direction, the form, the strength, and then you also want to mention any potential outliers. So you still have 4 things, but a different set of 4 things. Sometimes you'll hear outliers instead of using that word. Sometimes they'll use the word unusual features. So that would also be something kind of interchangeable with outliers. First up is the direction. When you talk about the direction, we're kind of looking at something almost like slope, what you would have been familiar with in Algebra 1. And if something would look like it would have kind of a positive slope, if you were to draw a line through it, then we'll call that a positive association. And then if it looks like it might have a negative slope to it, if you were to draw a line through the points, then we'd call that a negative association. Now, association is kind of a general term versus correlation is only for linear. So it's kind of like in geometry, how you had the general term quadrilateral, and then there were specific types of quadrilaterals like rectangles, kites, rhombuses, trapezoids. In this case, association is a general word, which means there's some sort of a pattern, and then correlation specifically means a linear pattern. So here's an example of a scatter plot, and we want to describe it. Now remember, we need to talk about direction, strength, form, and unusual features. So for this one, if you were forced to draw a line, your line might look something like this, which is why it's negative. Now, in terms of its strength, we're going to learn some rules pretty soon about what makes a strong or a weak relationship. But for now, if you had to draw a line, you would draw it something like that. You can tell it's obviously not a very good line, but it does have a negative association. Now, really, not really a line, a curve might be better. So in terms of form, for form, you would either say that it looks linear, or it looks curved, or it looks quadratic if it looks like a parabola, or it looks exponential or logarithmic. So think of your function families from Algebra 2, and that's how you'll describe the form. Now, in terms of unusual features, you can see that you've got kind of almost 2 separate clusters. So that's what I meant when I said that sometimes it's not just outliers that we're looking for, although there are definitely outliers here. Maybe this guy's pretty far away from the others, but also unusual features. So you see almost like two separate clusters of data would go into that part of your discussion. So here's another example. In terms of the direction, if we were to draw a line as best we could through these points, it would have a positive slope. So we'd say the points per game increase as the winds increase. So that would be a positive association. Form, this one does look more linear than the last one where we saw that curve. So it looks like it's fairly linear. And our strength, again, we're going to get some rules for that later, but they're pretty close to being aligned, so we're going to say it's fairly strong. Notice, just like we did back in chapter 4, we're using a lot of ly words to kind of soften our claim here. So it's fairly strong. So ly words are good to kind of soften your claim. You don't want to be too certain about how you say things. And overall, there doesn't seem to be any points that seem like they're really far away from the line that you would draw through here. One comment before we move on. Earlier in the year, when we were talking about one variable, there was a very clear formula for outliers, and you could tell with certainty whether or not something was an outlier. For two variable data, there's not really a formula. We'll get some definitions more clearly of what makes an outlier a little bit later on. But for the most part, you're just going to make an argument. But there's no definitive formula for outliers when you have two sets of data.